చూడు. ఓకే. ఓకే. చేసా. సార్ వస్తుంది సార్, అంత బాగా. మీరు 11కి స్టార్ట్ చేసేయండి సార్. ఓకే సార్. నీకు ఇక్కడ మాట్లాడుతుంది, అక్కడ వినపడుతుందా? వినపడుతుందా? నా వాయిస్ వినపడుతుందా నీకు? అక్కడ మాట్లాడండి.
Good morning, everybody. Welcome to the webinar series of International Training Center for Operational Oceanography. As you all know, since the pandemic, we have been conducting courses both online in terms of training as well as when our time permits. We are trying to get some experts in the field and trying to deliver some beautiful webinars. So as a part of this webinar series, today we have Dr. Vinu from Indian Institute of Tropical Meteorology, Pune. Some of you might be already knowing about Dr. Vinu, but it's my duty to introduce about Dr. Vinu to those who are trying to hear him for the first time. Dr. Vinu did his MSc in Physical Oceanography from Cochin University of Science and Technology. Followed by that, he has done his PhD from Hokkaido University, Japan in 2006. So after his PhD, he has been a postdoctoral fellow at National Institute for Environmental Studies for a period of almost 5 years. So after this postdoctoral fellow program, he has joined IITM Pune as Scientist D in 2011 and then continuing as scientist there, coming up with some very good works in terms of biogeochemical applications, and he has been publishing quite good number of things with the data that has been part of the Indian Ocean. And I would like all of you to hear from him on today's topic, that is an observational system simulation experiment that which we call OC for the Indian Ocean surface pCO2 measurements. This is already published and some of you might have already read this, but I feel hearing from the person who has been involved in this research would be much more wonderful. You will be allowed to chat with him with your questions, but of course all your questions will be answered at the end of this particular talk. Now I call upon Dr. Vinu to go about with his presentation. Thank you.
Thank you, Dr. Uday, for a very nice introduction, and good morning all of you. So I welcome all of you to this webinar. As Dr. Uday has mentioned about the background of the work, so I do not need to mention it again. So today I'm going to talk about our recent work about surface ocean carbon cycle in the Indian Ocean, an observing system simulation experiment for Indian Ocean surface pCO2 measurements. So I have seen the people who are the list of people who are participating in this webinar. So a lot of I mean the background in oceanography and allied subjects are with you, I mean among the participants. So I will make this presentation as informative as possible. So if you have any specific doubts or questions regarding this work or in general related to the carbon cycle, you are free to post it in the chat as Uday was mentioning. So I myself, Vinu Valsala, and this is a collaborative work done by a few people involved, as seen in this slide. And Sriyush, who was our research associate with us a few months ago, and another student Anshu, and then another scientist Srinivas here, and Dr. Yogesh from CCCR IITM. Dr. Kunal, of course, from INCOIS is involved in this work, and Dr. Siji from SPL VSSC Trivandrum. So I will go to the talk by introducing this aspect that the oceans play a vital role in mitigating the global climate change by sequestrating nearly 30% of anthropogenic human emitted carbon dioxide per year. So if you can see in this screen, the top right panel is a very familiar picture for you, the so-called Keeling curve. So it is nothing but the observed atmospheric CO2 concentration from Mauna Loa site since 1960s and until now. So you can see that the atmospheric CO2 is steadily increasing. We all are aware, so that is the central part of our global climate change and global warming. So you see that they are quite non-linearly growing in the concentration with a with a specific seasonal cycle for every year. See, for example, in the red color curve, and the annual mean line is shown as the black. You see that there is a steady growth of atmospheric CO2. So the atmospheric CO2 is built up due to the anthropogenic activities. However, you should remember that although we emit around 10 petagram carbon per year to the atmosphere, not all this carbon is staying in the atmosphere. The terrestrial biosphere of the Earth system is absorbing nearly 25 to 30% of it every year, sequestrating, and ocean do another 30% of absorption. So remaining 50% only what is seen in the atmosphere. Okay. So the idea is that if the ocean and terrestrial biosphere, if they are not absorbing that many carbon dioxide, so in the absence of this thing, the accumulation of man-made CO2 in the atmosphere could have been amplified by a corresponding magnitude, and our global warming would have been much more accelerated. So we should view in that point so that we can appreciate how the global oceans and terrestrial biosphere helping to mitigate or to offset kind of ongoing global warming to a less intensity. Now, the global ocean has sunk up nearly or taken up nearly about 165 petagram carbon emitted since the pre-industrial era. So that's quite a good quantity that ocean has naturally taken up to its interior. And the contemporary global ocean CO2 sink is estimated to be roughly 2.5 petagram carbon. So that is a recent GCP update. So now, so what about the Indian Ocean? So this is a global scenario. So let us focus today's talk more on Indian Ocean point of view. So tropical Indian Ocean alone contributed to storing roughly 16.6 petagrams anthropogenic carbon, which amounts up to 16% of the global total sink. So tropical Indian Ocean is not a huge area compared to Pacific or Atlantic or other mid-latitude and high-latitude oceans. We all know that, right? It's a small basin, but still its contribution is around 16% to the global total storage of anthropogenic carbon. And so there are various estimates exist in the literature. How much is the sea to air CO2 flux exchange between the tropical Indian Ocean and the atmosphere per year basis? Okay, so these estimates are shown in this table, for example. So these estimates differ based on the methodology one adopt. For example, I can say a synthesis of top-down and bottom-up approach has been summarized by Sharma in 2013, his paper. And they suggest in that paper it suggests that roughly Indian Ocean around north of the 40 degree north is around north of 40 degree south is around minus 3.7 petagram carbon per year sink. And however, the climatology surface ocean pCO2 based direct measurements, the kind of ship based pCO2 interpolated into gap filling and then basin wide, and then if we estimate as per the Takahashi et al. Data, it gives around minus 2.5 or 2.4 petagram carbon per year. Other estimates such as neural network self-organizing map-based estimates by Lancaster suggested that Indian Ocean is a much less sink, around minus 0.17 plus or minus 0.12 petagram carbon per year. Similarly, our own work in the past, say using a variational assimilation of available surface ocean pCO2 measurements in a biochemical model, we proposed in Indian Ocean to be a sink of minus 0.28 petagram carbon per year. So where is this estimate differ their net quantity of a sink of Indian Ocean carbon, Indian Ocean sink according to the method and the availability of data in particular approach. Okay, so this is one critical issue that we need to fix or constrain the Indian Ocean much more in its net seasonal cycle as well as in other time scale variability. What is actually the sink or the source of Indian Ocean, and what is the uncertainty exists to how we can reduce this uncertainty in the present day sink or estimate. Okay, so now before going further, let me give a very brief introduction how actually the upper-ocean carbon cycle works. What are the very fundamental elements involved in it? So I represent it through a very schematic cartoon here. As you can see, this represents the ocean and separated from the atmosphere. So what happens in the ocean? So upper-ocean carbon cycle contains a few elements. So one of which is the exchange of carbon dioxide between the atmosphere and the ocean. So why there is an exchange? Because atmosphere has a specific quantity of partial pressure of carbon dioxide for every given volume of air. So does in the ocean. When the CO2 dissolves in the ocean for any given specific volume of water, which will also have a carbon dioxide partial pressure. So once these partial pressures has a difference, then that tries to expel the gas from one system to the other. So it all depends upon how much delta pCO2. We call it the difference of partial pressure as the delta pCO2. So according to the delta pCO2, the carbon dioxide gas will be exchanged between the atmosphere and the ocean. It is a two-way process. I mean, wherever the oceanic region, where ocean water has higher pCO2 than the atmospheric pCO2, then definitely gas will be exchanged from the ocean to the atmosphere and vice versa. Okay, so why and to act for this phenomenon to occur, the turbulence is the basic mechanism. There has to be an exchange of properties across the ocean air interface. Definitely the turbulent fluxes becomes important, or gaseous exchange. How, therefore the role of wind is important, and the solubility condition of carbon dioxide gas in the water is also important. Solubility of a gas in water, we all know, who knows chemistry knows that the function of temperature, ambient pressure, etc. And the dissolved content in the water as such, this depends upon that the solubility will differ. So according to solubility and the wind conditions and turbulent conditions and or AC exchange conditions, the gases, carbon dioxide will be exchanged between the atmosphere and ocean. So that's the part of shown in the top left panel of this cartoon. And within the ocean, however, what happens, we all know that the upper ocean is a very biologically active ocean because we have a reception of sunlight and we have dissolved inorganic materials available in the ocean, and the phytoplanktons living in the ocean using their chlorophyll content and the insolations of solar insolation and available nutrients, they produce biomass. So the biomass can fix the dissolved inorganic carbon into bioorganic form, and this bioorganic forms fix the dissolved form of carbon in the upper ocean to its biological form. So this biological form further export downward. So this downward export of biological matter kind of export net carbon interior below the upper euphotic zone. So this is a biological component of the carbon cycle in the upper ocean. So the earlier component, which is air-sea exchange, we can call it as a solubility pump. Okay, the pump means that it is a net absorption of carbon from the atmosphere to the ocean. So which operates due to the chemical solubility and wind exchange. However, within the ocean, in the upper euphotic zone, the biology takes up the role to synthesize the carbon into its body and export downwards. We call it a biological pump. Biological pump further may divide into soft tissue pump and hard tissue pump. I'm not going into details of that. Then what happens once these particles are exported downward? Below the euphotic zone, there is no more production, and because there is no more sunlight to support a production, so the bacteria will start to decompose or remineralize this exporting material, right? And this, due to this remineralization or respiration of bacteria, oxygen will be consumed, and the nutrients will be returned back to the ocean as an inorganic form. So this biological export basically transfer the net dissolved organic or dissolved nutrients in the upper ocean to the interior. But if this mechanism goes on in one directional, what happens after some time, the surface ocean will get depleted with the nutrients and carbon, but that has to be replenished. So what happens? So then the dynamics of the ocean comes into picture. It due to the the dynamics of the ocean is such as the upwelling, the entrainment or mixing or very deep mixing, upwelling, etc. These interior deep rich decomposed nutrients will return back to the euphotic zone and the cycle completes. So this is called as a biological pump within the ocean. So both solubility pump and biological pump is contributing the regulation of or governing the net carbon cycle in the upper ocean. And not all the dead materials, however, return back to the ocean. Some of it those are heavy, and for example, there are shells and skeletal structure. They may still sink to the interior permanently and buried in the sediment. So that part may return back to the ocean after enormous amount of geological time scale. It's not very easy to return. But other soft tissue pumps and other dissolved matters, remineralized matter from the calcium part, for example, return back to the interior or intermediate depth of the ocean, and they will be returned back to the surface due to the dynamic return or due to the dynamics. We call it as a new production, for example, the upward return of nutrients. So this is a very fundamental structure what carbon cycle is operated by these two fundamental pumps in the upper ocean. Okay, so now let us come back to the picture of the Indian Ocean. So what is the C2 or CO2 fluxes based on the available observation of Takahashi et al. Climatology is telling us about the Indian Ocean carbon fluxes. So this picture shows the 4 seasonal aggregate of C2 air CO2 fluxes. So what is means C2 air? That means the carbon dioxide outgas from ocean to the atmosphere. So whenever you find a positive value here, the carbon dioxide is outgassing, and whenever you see a negative value here, the carbon dioxide is sinking to the ocean. So if you look at the seasonal cycle of the Indian Ocean, the extreme seasons such as December, January, February, and JJAs. Let's go by season. In November, you see Indian Ocean to be a mild source, more or less, in the tropical area, which is continues to be a situation in March, April, May. However, Indian Ocean tends to be a heavy source of carbon dioxide to the atmosphere, especially in the western part of the Arabian Sea, where you have a summer monsoon related upwelling at the Somali Arabian coast. So upwelled water will have carbon rich water, will be carbon rich, because as I said earlier, the exporting material downward will get decomposed at the intermediate depths, and that depth will have a rich in carbon dioxide or dissolved inorganic carbon. So when the upwelling happens, all this water comes to the surface. Okay, so the upwelling increases the C2 air CO2 flux in the JJAS in the western Indian Ocean or western Arabian Sea, for example, which kind of again get diluted by October, November in the following season. So more or less in an year round, if you take 20 degree or 10 degrees south or north of south and above of the Indian Ocean, you find Indian Ocean is acting as a source to the atmosphere. So this is the natural cycle of the carbon air C2 air CO2 flux of the tropical Indian Ocean, as per the Takahashi et al. Takahashi et al. Observation. So this observation, however, is not done with meticulous scanning of the entire part of the Indian Ocean, because the observations are very sparse, collected by, I am coming to that in a while. So they are heavily interpolated by looking at other proxies such as temperature to SST to pCO2 relation. So that relation also used to interpolate and arrive in such a map, for example. Okay, so now, so this is the slide actually talking about the present scenario of surface ocean pCO2 measurements from the Indian Ocean. So this map is compiled from the SOCAT database, which is SOCAT latest version, 2020 version database, which total consists of 95 million quality control surface pCO2 measurements, okay, available from 1970 to 2019. But Indian Ocean shares only 0.8 million out of this 95 million. So that means it hardly represents 2.8% of the total quality controlled global pCO2 data. So Indian Ocean hardly even representing 2.8% or 3% of the total data available, which itself shows how sparse is. Now for the top panel shows shows the locations we have sampled the ocean, Indian Ocean, for the pCO2 measurements in the last 30 years, for example, or 30 or more, 40 years, from 1970 to 2020. If you look at this scale, if at all a measurement has reported a quality controlled data, that data has gone into this database. Okay, so therefore this tracks may look like it's kind of filled, but remember, this has been compiled from 40 years of data. So it is not at all a great coverage, considering maybe one track might have happened at one time in the past, and that track never repeated in the history, for example. Okay, and most of the observations, and this is a kind of a total observation dots in the log scale shown here, and the bottom panel shows the total time, the time duration and the number of kilo observations available for this domain, for example. And we see that there is a density of observation happened in between 1990 and 2000. That is the Jagov's era, where over the world ocean circulation experiment related activities and subsequent Jagov's era has scanned the global oceans, and part of that Indian Ocean also has been scanned for the pCO2 measure. So the majority of those measurements came from that Jagov's era, which is again happened in the middle of 1990s. Okay, so now after that you see there are very sparse observations only happened in the Indian Ocean. So that means if you take, say for example 2015 or 2016 annual mean observation locations in the ocean, you will find one or two lines only in the Indian Ocean. You will not find any observation. So we are having a severe lack of observation in the Indian Ocean in terms of surface ocean pCO2. So these are some key points we have to comment here. So despite being the third largest global ocean, the inadequate data coverage of the Indian Ocean hampers the accurate renditions and budgeting of its carbon cycle. Okay, so it perhaps not much felt in the seasonal cycle, because seasonal cycle, once you constrain with past observation, you can kind of make a robust cycle, and then we can rely on that. But it affects, so therefore this lack of data perhaps not much felt in the seasonal cycle, but it affects the reducing the very subtle year-to-year changes and large scale changes like decadal change, variability, etc. cannot be constrained at all with the existing set of observations. There has been, however, even this is in place, there has been no effort made to sample pCO2 by any underway sampling using volunteer commercial ships in the Indian Ocean. Unlike it is practiced in the Pacific or Atlantic, you don't find such an effort in the Indian Ocean. So therefore, it leaves a significant data gap in the Indian Ocean, especially north of 30 degrees south. So this is what the existing scenario. Now, what are the questions we can pose here is that the surface ocean pCO2, it can be measured by instrument mounted on to moorings, for example, or attached to the hull of a ship, for example, in the underway sampling case. Now, then if we are trying to do such experiment, there are two important question arises. So one such question is that which existing mooring in the Indian Ocean where we can install the instruments for pCO2 measurement most cost effectively. So in all the aspects, one has to, I mean, the operation cost also should be minimum, or in other words, this data what supplied by this observation should be effective in reducing the uncertainty in some of the estimate regarding the upper ocean carbon cycle of the Indian Ocean. Okay, so that value addition should be there when we install an instrument, for example. And second question is, suppose we are trying to operate a ship of opportunity program for sampling the pCO2 from the Indian Ocean. Which ship track should be selected for the underway sampling? There can be several ship tracks in the Indian Ocean, commercial ship lines we can identify. So among these, which track is the best track, so that the data obtained is most effective in constraining the Indian Ocean upper ocean carbons or Indian Ocean upper carbon cycle. Okay, so that is the kind of questions unanswered so far. So now, saying so, we should highlight the effort of INDOOS-2. But what is INDOOS-2? It is Indian Ocean observing system. So INCOIS is the central part of the INDOOS-2 in the Indian from the Indian contribution. So INDOOS is the sustained observing system for the Indian Ocean, a network operated and supported by various national agencies and coordinated internationally under the global CLIVAR, for example, Indian Ocean panel. And INDOOS has updated their priorities into actionable recommendations for future observing system components and put forwarded the recommendation for an effective observational program of the Indian Ocean. So this document has been released in 2020 when our research was ongoing. So this is kind of their cover page of INDOOS-2 report. People who are interested can go and read, and this is a wealth of information. Okay, If you read this report, I think if young people are listening to this talk, if you want to get one book view of entire progress happened in the observations and the future proposals of the Indian Ocean, you better read this document. It's a wealth of information with a lot of references and citations, etc. Now, so Indus 2 has their wish list in this 2020-2030 actionable plan, and taken from one of the chapters of this report. So this is what they are proposing. They have to, and the dots here shows, the green dots shows the Argos, which is bio Argo as well as the deep Argo, and there are moorings shown in the diamond shape. For example, you can see in the central tropical region of the Indian Ocean, you can see there are moorings which is shown as diamond, which is Rama mooring, and then there are XBT lines, which is repeated lines shown as red color, and tide gauges are shown as cyan dots, for example. Tide gauges. Surface drifters are also proposed under this in this color code, and boundary current array, and so many observational efforts has been shown in here, and Go ship is also shown in some tracks here, for example. So what is interesting is that this is their wish list, that Indian Ocean has to be filled up with, say, 200 number of Argos in the next 20-30 time scale, which is one of the highest side in the wish list they're proposing. However, there has been no effort made even in this report that if we are targeting the pCO2 measurements here, where actually we should start measuring pCO2, so that the data will offer a best constraint for the carbon cycle of the Indian Ocean. So now, despite the strong recommendation under Indus 2 in place, only one of the existing Rama mooring in the entire Indian Ocean is equipped with the sensors for making surface ocean pCO2 measurements. So that is located in the central Bay of Bengal. This Rama mooring at 90° east and 15° north. Yeah, so this particular mooring has a pCO2 sensor installed with pH sensor also. They are giving data from 2013 to today, but there are data gaps, and even in recent past the data is not updated. So this is the only mooring we have the sustained pCO2 observations among the entire Rama mooring array so far. And other than that, there is no other mooring equipped with the pCO2 sensors. So, but in the other aspect, if you look at the anthropogenic pressure in the open ocean offered by the ship tracks in the ocean from satellite altimetry, there's a nice article published in 2014. You can see this is the major ship routes in the Indian Ocean. Okay, so Indian Ocean has two major straits in the east and west. One is the Malacca Strait, through which the major shipping lines are coming out and then going to the Suez Canal in the west, and because of these two major channels sitting in the both sides, so there is a large number of ships passes along Indian Ocean, and that can be seen by looking at this particular picture. So Indian Ocean also has potential to offer certain ship of opportunity program. So what is a ship of opportunity program? Some voluntarily some ship line may participate in installing instrument on our behalf, and they make routine monitoring in their regular circuit. They routinely monitor the upper ocean properties, including pCO2, alkalinity, and temperature, salinity, etc. So if such an operation starts in the Indian Ocean, that's where a lot of data will be coming up from that, and that can be utilized for constraining the model in any modeling framework. So anyway, these are the major ship routes revealed by the altimetry data. So we are also asking a question in this particular work: if these are the number of ship routes, which ship route is the best one? Suppose one wish to start a SOOP operation, ship of opportunity program. We call it SOOP, SOOP operation in the Indian Ocean. So that question also we address here. So now, if you look at that, once we have such data, see, if you look at if this particular picture is taken from the SOOP, SOOP program, so ship of opportunity program pCO2 lines in the world, for as a summary of 10 years is shown in this particular panel in the bottom left. So what you see that how the North Atlantic and North Pacific, they are covered with heavily densed such lines. That means they have data every 2 weeks crossing by the ship crossing the entire Pacific from the East Pacific to the West Pacific. So such a data is very important for modelers, for example. In North Atlantic also, the coverage of voluntary ship pCO2 observations are enormously large, and There are also some lines in the Southern Ocean, and some are research cruise lines. It's not voluntary ship lines. However, and also there are many bioargos installed in the Southern Ocean also to monitor pCO2 also. But if you look at the Indian Ocean, this is a kind of a 10-year summary. As I say, hardly any data. So you don't find any data to constrain the Indian Ocean in the, say, for example, 1980 to 2020. Somebody wants to really constrain Indian Ocean in a model. We have hardly any data. Okay, so this is actually felt in our own effort in previously when we tried to assimilate the surface pCO2 into a biogeochemical model. This is one of the first effort in the globe where a variational method of is used to assimilate surface ocean pCO2 into a biogeochemical data. So we come up with a mean map after assimilation, and we are very confident that the North Pacific and North Atlantic got well constrained in the model, but the Indian Ocean, however, is not had no chance to constrain better because we had hardly any data. So the point is that if we have such data available, the technology is already existing, so that to assimilate them into the model, so we can build a confidence in the robustness of the upper ocean carbon cycle of any particular regional ocean. Okay, so that's the benefit of having more data for the research community. Now, so in this context, the emerging questions, what is the best track to start the ship of opportunity program in the Indian Ocean? So we note here that the Indus 2, one of its recommendation include the establishing SOOP CO2 measurements in the southern oceans in the 1x21 repeat track. Whereas the other potential SOOP tracks remains unexplored. So the Indus also is not explored well with this kind of ship tracks, and which ship tracks one can depend, etc., are not explored so far. So therefore, the present study, we are addressing the gap mentioned in the above areas by answering the following key questions. So what are the questions we are asking here is that what are the optimal mooring locations of Rama and Omni? So we are not forgetting Omni here. Omni is a kind of dedicated program by the Indian government and operated mostly by NIOT. So they also have a the moorings in the Arabian Sea and Bay of Bengal, covering the peninsular Indian region. Rama and Omni we are considering for making pCO2 measurements. Now, what is the potential bioargo float? So bioargo is another recent advancement in observing the carbon cycle is through bioargo. So bioargo offers surface ocean pH measurements, also the profile pH measurements, which can be converted into pCO2 and can be used for upper ocean carbon cycle research. So we are also looking what is the potential of bioargo floats in replacing the moored buoy inserts in the future. Because bioargo may in one way it may be advantage because it can increase in number without any constraint on or restriction on the location, but it may have a disadvantage regarding the cost effect and quality, etc. So it can be debated, however. And the fourth question we are asking is the third question we are asking is what are the potential ship of opportunity tracks in the Indian Ocean for the measurements of surface ocean pCO2. So now the task is that the OSSC, we need to conduct an observation system synthesis or simulation experiment. So in any OSSC, what you fundamentally do is to reduce a cost function. So what is cost function? It is an accumulation of errors in the model or in a particular component of the model. For example, here we constituted a cost function as that there is a certain error in the flux estimates as well as there is error in the model with respect to the observation. So our cost function will have two components, the model error and the observational error. So we have a model error and a flux error. So our purpose of this OSSC is that we have to place instruments in such a manner that our flux error is minimized. Okay, so we are trying to constrain or limit the flux error based on this cost function. So here S0 represents the prior C2 or CO2 flux. So we are assuming that suppose in hand you are having a prior estimate of a C2 or CO2 fluxes and with some observational error variance covariance of the upper ocean carbon in terms of dissolved inorganic carbon, and you have a prior flux, also you have a prior flux variance covariance structure with you. Now what will be, and some observation D is available, then what will be the best estimated flux S. So that is what we are going to calculate. So S is the posterior C2 air flux. So this is our cost function, and we are going to minimize this cost function using placing some instruments on this mooring. So what are the mooring we are considering? We have considered the Rama mooring, all the mooring, despite whether it is in operation or future operation or not in operation, we consider all the Rama mooring and Omni. Omni you can see in the Sian line covering both the peninsula region in the Bay of Bengal and the Arabian Sea, and we also consider few major ship tracks. Okay, these ship tracks we sampled by looking at the anthropogenic pressure in the altimetry data that has published in 2014. I show you that picture earlier. We sampled a few tracks and named them track 1, track 2, track 3, and considering which of this track is the best track for a surface, or sorry, for a ship of opportunity program for measuring the Indian Ocean pCO2. And we, in addition to that, we also consider bio-argos are placed everywhere in the Indian Ocean at a 10 degree by 10 degree tile. Suppose you are implementing bio-argo in such a density, what is its benefit? Considering the installing mooring, the sensors in the mooring, what bio-argo has additional advantage or benefit? That also we investigate under this research. So now the methodology we are adapting is rather simple. We adapt the Bayesian inversion. So what I will introduce briefly what actually the Bayesian inversion. I think it is the essence of this inversion is similar to any cost function reducing problem as we see in the data assimilation through either Kalman filter or variational method. So the basic is coming from the least square method, which says that if you have a cost function constructed with model mismatch and the flux error in your system, it can be minimized if you constrain the problem with observation D in a manner that your posterior flux will look at with the prior flux S0 with these correction terms. So this correction term has to respect the data minus model mismatch. To reduce this data minus model mismatch, you need to have a proper variance covariance matrix. So the minima of the function is achieved in this form. So if you learn the theory how the least square method works and the minimization algorithm, then you understand that the posterior flux will be equal to the prior flux plus certain correction terms. So I'm going to introduce each of these terms in the subsequent slides. So here GS0 represents the model response vector corresponding to the observation D. D can be pCO2, or you can convert pCO2 into dissolved inorganic carbon, because pCO2 is not a prognostic variable. Okay, it's a kind of a diagnostic variable in the model. So GS0 represents the model response vector corresponding to the observation D, and S0 is the prior C2 air CO2 fluxes. So you have to give some prior assumption. So this is the shape of my air C flux. So asking of system to correct it with available observation. Okay. Now CD is the observational error variance covariance matrix, and the CS0 represents the prior flux variance covariance matrix, and S is the posterior, that's the outcome of this exercise, and D, if D is the observation available, which is from pCO2, for example. Now, how this Bayesian system work is that we divide, unlike the Kalman filter, where it depends upon the ensemble, or variational method, which depends upon the adjoint model, here we use a much another way of approach. You can call it like a semi-ensemble approach. Here, what we do is we divide the ocean first into certain defined regions, region 1 to region 8 or region 1 to region 10. And this region can be demarcated by looking at certain homogeneity in the biological or biogeochemical component of the ocean. I'm coming to that in a while. Suppose, and if you divide the ocean into such well-defined regions, now what we're going to do is that we can perturb the biogeochemistry model by implying certain amount of known flux through this region. So I am going to inject 1 gigaton carbon per year for a particular region, and I'm going to simulate my model for 10 years or so. Then what will happen to this artificially injected carbon to the ocean? They are going to propagate into various parts of the ocean by respecting the governing fundamental dynamics, by governing the biogeochemistry of the system, right? And the RC exchange of the system. So by means, this extra carbon injected will be propagating in the 4-dimensional space, space and time, and arrive in your mooring location. Okay, so this mooring, which will sense an error imparted, or a perturbation imparted through a particular region, after some time is going to be sensed by the mooring. So this is the first task of this inversion is to arrange the G matrix, which is the sensitivity matrix or the model response matrix or the Gaussian function, whichever way you can call. So the G matrix will have element for Oceanic region R1. and observation location 1 will have some element arriving from this region 1 through this due to this perturbation, which will mark it as an element 1. And suppose you have another mooring situated somewhere else from this region 1, they also sense how much the propagation has arrived from the perturbation to that region 1. So it will be recorded in that mooring. So all the mooring you can align in this row, and all the regions can be aligned in this column. Then you will get the elements of the G matrix. So what is this G matrix? It is actually the sensitivity. That means if you have a control experiment, you have a perturbed experiment, if you take the difference, that difference will tell how much of this perturbation given to any particular region has been sensed by a particular mooring in a well-defined faraway location. So if you have this model sensitivity matrix, which is the first step that you need to have a Bayesian inversion. Okay, so here we simulated the model in forward mode, for example from 1996 to 2005, and this red curve shows the delta DIC, I mean the change in DIC due to the artificially injected perturbations. Okay, so that will arrive at a mooring location over the time. So we take after a 9th or 10th year of the simulation, this is the part in time we constructed the G matrix, because we should allow the errors to propagate into a certain direction, and then only we can sample it, because the life history of carbon within the ocean is in the surface it is 6 to 1 months to 1 year, but interior can be much slower. So we kind of adapted for upper ocean to be nearly 10 years of simulation, and in the last year we sampled the elements for the G matrix. So this is how the fundamental or the simplistic explanation how Bayesian inversion works basically. So what you need to find is the elements necessary to solve this equation, and the most important element is the G. I have already explained how you sample the G matrix for this inversion, and the rest are the variance, covariance matrices and all. I'm going to explain how we can construct it. Okay, so now, so what Bayesian inversion says that if the optimal flux is S with the S naught as the prior and the correction term offered by these many terms in the right hand side, now this term on the box shows the posterior flux uncertainty. So after constraining the model with available observation, there will be a remaining uncertainty, which we call it as posterior uncertainty, which can be obtained by the combination of terms in the red box. So what are they? So like G transpose CD inverse, G plus ES naught inverse, etc. The interesting part is that to get this matrix, you don't need observation. Okay, so observation is far away from this matrix. You don't need real observation to calculate the posterior flux uncertainty. That is the basic idea of any OSSC. Okay, so therefore the OSSC, there is no requirement of observation, but rather it requires only the observation location. Okay, so why you need a location? Because to sample the G, you need to assume a hypothetical mooring. Okay, it's going to sample your perturbation. So that is only G, the location of the observation is only required. And you require a variance covariance matrix of the observation, also the flux. These two terms are required, and you don't need a data. You don't need real data. So that is the basic principle of the OSSC. So therefore for OSSC, there is no requirement of observations as such, but rather we require only the observation location. So this is the basic principle we use in any OC experiment. Okay, now whether you do it through Kalman filter or do it through the variational method, this is the basic principle you use. So only need the location of the observation, don't need the real data. Now, so this is how the basic theory works. However, even if you have the theory, you need to have a minimizing algorithm to arrive the minima of the cost function. So we here depend upon a descendant algorithm approach. So descendant algorithm is nothing but, suppose we have so many potential observational moorings are with us. Okay, we can call all of them as the candidate set. So all are candidates for installing pCO2 sensors. Now we need to start with which of this mooring is the best mooring to start the observation. Okay, so what we consider that we minimize this particular cost function, and we look for the posterior flux uncertainty, assuming each of these argos are independent. Okay, so we have n number of moorings. I'm sorry, it's mooring. So we have n number of mooring. We call it as candidate set, and the best set is 0. In the beginning, we don't know what is the best mooring. So what will happen is that we will first start, minimizing this minimizing this cost function, assuming there is each of these mooring has pCO2 sensors, and each of these mooring will be used to minimize the cost function independently. So you will get the best mooring out of that experiment. So, and that mooring you will move to the best set. And so one mooring got moved to the best set, and your candidate set now reduced to n minus 1. Now what will you do? You add one more mooring to the best mooring, and redo the experiment. So and one by one, okay, one by one you add it to the best set, and again redo the experiment. So then you get which is the best combination of two mooring, giving the uncertainty reduction, or this term better. So like if you consider this procedure, so that all your candidate set get added to the best set, and the order in which they get added to the best set is their ranking. Okay, so the first rank mooring will get added first, and the next rank mooring will added next, and you will you will continue this in an incremental manner, so that all the mooring will get added to the best set. So you will know what are the best mooring to focus. So that is what shown in this schematic here. So if you have a total potential stations n or moorings n, so you calculate the uncertainty reduction offered by each station separately, and find out the best station with the maximum uncertainty reduction, and rank it as 1. So the remaining station thus become n minus 1. Okay. Now add one station by one station to the rank 1 station, and calculate again the uncertainty reduction in the fluxes as a combination of two stations. Find out the best combination and with the maximum UR, and then rank that station as 2. Then you continue this process, so that all the candidate set get added to the best set. So this is called the incremental optimization. This is like a time consuming algorithm. There can be better algorithm than this in a Kalman filter or in other method, but this is what we adopted. And so you have to repeat this algorithm according to as many number of moorings. So we have only 43 mooring in our hand, and BioArgo we had around 52 or so for every 10 degree Indian Ocean grid. So what we'll look up at the end is that if as the mooring number increases, the uncertainty reduction in the flux estimate will increase, and it saturate after few moorings. So after that, even if you add more mooring to the system, it's not going to benefit much, because its system reaches the saturation, and the remaining uncertainty is by virtue of not due to lack of observation, but the lack of the demerit of the system itself. The model may have error, representative error, so that also contribute to the uncertainty in the estimate. So we will reach a point we are helpless beyond when improving the uncertainty reduction beyond a point. Okay, so this is a basic theory. Now, to do this, what you need is a decent biochemistry model you need, because that is the model which will be constructing this, this G matrix or the sensitivity, the model response. To have a model response, you need a fully, functioning biogeochemistry model, because this biology has to govern the system, and chemistry has to govern the system, the ocean dynamics has to govern the system. So you need to have a ocean biogeochemical model. So now let me introduce what is the model we used in this purpose. So we use the ocean tracer transport model, which is working at IITM for last several years. So this is this model is developed a few years ago by our own research. So the basic element of this model is that this is developed from an ocean tracer transport model, and it has a Oceanic 2 type biogeochemistry embedded in it, which is what shown in this cartoon here. And it has we have done a good amount of research on this model to modify its parameterization, so that the simulated air sea fluxes are having a less bias compared to the observation. So we have modified a few biological parameterization in the model. So otherwise, it's a offline tracer transport model. It does not solve its own dynamics, rather it borrows the dynamics from a reanalysis construct, say for example ocean reanalysis product, then evolve the tracer prognostically within it by solving the mass conservation, continuity, and etc. So now it has also the mixing parameterization embedded, because the vertical mixing is very important in any nutrient cycling in the ocean. Such mixings are parameterized by or incorporated in the model by mixing coefficients. So, but they are not readily available with any reanalysis product. So you need to have your own vertical mixing parameterization to include mixing processes in the model. So that is also incorporated in this model. So to talk about more on the Oceanic 2 pCO2 biogeochemistry. It's a nutrient restoration system. So if people are interested, they can read these papers and understand how the biogeochemistry is embedded in this model. So now this model also should have a C2 air CO2 flux calculation, right? Based on the solubility pump and river runoff fluxes and precipitation fluxes all should be incorporated. So they are reasonably incorporated into this particular model. So for validating this model, for any model require a validation, the transport of this model we validate using the chlorofluorocarbon inventories. Okay, so we can simulate CFC inventories in the ocean and we can validate it. So I'm not going into detail because this can be found by papers published from our group. So we simulated CFC and see how CFC compare between observation and model. So that's how we develop a confidence the transport of the model is all right, etc., etc. Okay, I'm not going to the details. Now this is the mean seasonal air sea flux simulated by this model in the from 1996 to 2005 during the experimental period. You see that I already introduced the JJS has larger emission from the Western Arabian Sea, and other seasons they have a mild sourcing pattern of the Indian Ocean, and this shows the surface ocean dissolved inorganic carbon from the model are simulated by the model. So the unit is given mole per meter cube. Okay, so this is shown as a mole per meter cube, and this is a kind of agreeing with the available climatological maps from the Boost cruises, for example, or the GLODAP data sets we compare, and it has a reasonable comparison with the observations. Now, to construct the next important part is how do you construct the uncertainty matrices. So that is very important also. So this the construction of observational variance covariance matrix CD. So we actually decompose them into two. One is the observational error and a model error. So in this setup, actually the pCO2 is assumed as converted to DIC, dissolved inorganic carbon, using the solubility routine. So that conversion will offer you some kind of error. So if you have an observational error of pCO2 of plus or minus 2.5 microatmosphere, which is a reasonable uncertainty in the pCO2 observations, you can convert them into equivalent DIC error. We taken it as an observational error, and the conversion of pCO to DIC will also incorporate the errors due to alkalinity, phosphate, silicate, and other temperature and salinity and another minor ion. So all those errors have been considered while constructing the observational error. And this is a particular seasonal cycle of observational error in the Central Arabian Sea by this conversion. The errors are having a seasonal dependency because, as I said, the pCO2 to DIC conversion is a function of the ambient environmental variables, say temperature, salinity, alkalinity, etc. So accordingly, the error construct will also have a seasonality within it. So this is a typical error variation in a Central Arabian Sea. The observational error pattern looks like this. Now the construction of the flux error variance covariance. So fluxes are prior fluxes. Okay, so we have some prior ocean fluxes in our hand from our previous research. So we can look at how these fluxes from region 1 to region 2 are varying. We can constrain certain errors to the fluxes so that we taken care from our existing air sea CO2 flux data from 1980 to 2009. So the diagonal elements here will represent the variances of the seasonal cycle, and off diagonal elements represents the kind of variances in the season, covariances in the seasonal cycle between each oceanic region. So that's how we construct the season flux variance covariance matrix. Now this is the coming back to the how many regions we used for inversion. We used 8 regions. So these regions are marked in this particular map. They are numbered from region 1 to region 8. So what are these regions? This region represents some kind of homogeneity. As you just consider it as some kind of homogeneity we identified for this ocean. And don't ask me how, because then I need to explain much more. So actually by we looking at how the compensation depth, that means the depth at which the community respiration balances the production. So that depth is taken as a key indicator, and look at how seasonally they vary. So accordingly we divide the ocean in this shape. This may kind of go along with the biomes of the open ocean. Okay, so that I'm not going into detail. Assume we have 8 identified oceanic region, and we have Rama mooring shown as the red and Omni mooring shown as the cyan color, and the star shows us the ship track. And this right panel shows the seasonal cycle of air sea fluxes from each of these oceanic region in petagram carbon per year, and their uncertainty is monthly uncertainty is also shown here. So these are the region, and these are the tracks, and these are the moorings we consider for optimizing them. So now I will show the result after optimization. So before proceeding further, you may be interested what does the G element looks like, I mean G matrix element look like. So this is the end product of the model sensitivity produced with perturbing each of these oceanic region with 1 petagram carbon sink. Okay, so this is how the injected carbon propagates in the ocean after spending 9 years within the ocean. So you see that the Arabian Sea injection has spread all the way in this direction. Bay of Bengal did not spread much because, as you know, Bay of Bengal is a highly stratified ocean. The injected air rather staying in there with slight propagation to the Western Arabian Sea due to these reversing monsoon currents. I think you all understand that fundamental dynamics of the Indian Ocean. The other regional perturbations kind of moved around, like through flow kind of region bring the perturbation all the way to the west and spreading in the Western Indian Ocean. But in the subtropical gyre, the perturbation more or less remains within the same shape as the perturbation zone itself. Okay, because there is a it's a converging zone with less dynamics. Okay, so they kind of remain within it. So this is the elements of this maps is going to the G matrix. Okay, so that's why I show here. So similar elements I reproduced for the model error also. So model error is produced along in the similar manner by perturbing the flux errors in those oceanic regions. So that's why we constructed the model error. So this model error and observational error will go as the total error in the model covariance, error variance covariance matrix. So now I come to the result. So in the OSSE, then the OSSE is done. So this is the result we got. So we what this picture shows the rank of all Rama and Omni mooring. Okay, identified for each season. So this is for December, January, February, March, April, May, June, July, August, and October, November. So this is the the ranking of these moorings identified for each season for surface ocean pCO2 observation, with the deep blue representing the best moorings one can go by, and the red color represents the not so valuable mooring. Remember, this ranking is considered for constraining the air sea flux of this domain, okay, from 40 degrees south to 30 degrees north, that domain. So constraining the air sea flux of the entire Indian Ocean, these are the mooring locations the ocean look for to have a pCO2 data. So that's how it should be interpreted. So let us pay some attention to the best mooring. So invariably Arabian Sea requires some mooring requires some pCO2 sensors, and some of these 10 degrees south to 20 degrees south belt also requires some mooring, and somehow the model says that the eastern equatorial Indian Ocean moorings will not add much value to the pCO, to the carbon cycle reconstruction in the Indian Ocean. So that is a kind of a striking result we got during this synthesis. And Bay of Bengal also capture some kind of blue to cyan line. That means they are also value adding moorings if you install the pCO2 sensors in there. So this is a kind of a ranking we have done for all the Omni as well as Rama mooring to install to initiate a pCO2 observation. Now suppose somebody wants to start observation, so they better focus on this blue to cyan colored mooring and go install a sensor there. So that sensor is going to give a pCO2 which is worth for constraining the error or minimizing the error in the sea-to-air flux of the Indian Ocean. Now, if you look at the picture of BioArgo, so I deployed BioArgo in a regular interval at 5 by 10 degree by 10 degree tile in the entire Indian Ocean. So the locations of BioArgos are different from mooring, and for each season, these are the value addition brought by the BioArgo. To be consistent, that Arabian Sea BioArgos appears to be highly influential, and in the belt between 20 degrees south is becoming influential, but the non-influential mooring BioArgos got slightly shifted to the zone that than compared to the mooring, because these Argos are, their initial positions are much more different than the mooring, so they have slight disorientation. But you see that equatorial to southeast, this region shows kind of a less value addition, which was consistent in the earlier also. if you could see. But some moorings got higher value in this particular part, and that actually happens so because it is representing for these bioargos, because it is finding the closest mooring, because there is no mooring at that 20-degree belt of Rama mooring. So they are trying to find the closest mooring and put a better value for these argos. But the real picture becomes more clear if you distribute bioargo in a uniform shape. So so this is what the bioargo value addition will look like. The best bioargos are the blue colored, and the less value addition bioargos are the red color. But here you have to understand one thing: the argos are not going to stay in a particular position; they are going to move around. So the assumption we used, even if one argo move from right to left, the other argo going to replace from the neighboring grid. So kind of a uniformity may be maintained for a few years. I'm not very guaranteeing that it will maintain like this for the whole life history of that bioargo. But anyway, this is the ranking of the bioargo we have done. And these are the uncertainty reduction offered by the combination of Rama and Omni. The maximum uncertainty reduction for any season, okay, is brought by around 15 or 12 moorings, up to a 30% only. So that much only mooring can help in constraining the Indian Ocean air sea fluxes. But bioargo can constrain even more, because bioargos are widespread. They are not location specific, that they are deployment specific. How you deploy, that will determine, right? So up to 53% can be uncertainty reduction can be achieved by around by 20 bioargos. So that means that's what we are saying. Bioargo can be a sufficient replacement for the mooring based observation of pCO2. So this is again can be scientifically argued, because deployment and cost etc. is another thing, because the economical constraint we are not considering in this OSSC. Only scientific constraints are considering. Now coming to the ship track, see that these are the best ship track if you wish to start an SOOP program for the Indian Ocean. The rank number 1 is taken by, this is shown for June and January and July. The rank number 1 is from this Australian Perth to going to the Arabian Sea, and this may be quite impractical for India to operate, or some other shipping companies may come forward to offer it. And the ranks are quite consistent even if you consider the seasonal changes. And the maximum efficiency is that around 60% or more efficiency is there for a ship track, because that much uncertainty will be reduced by a ship track, because ship track is quite long. It covers in a matter of 2 weeks the entire Indian Ocean, so it can give you quite consistent amount of data, and it is a repeated data, right? So that can give you much more constraining the basin than individual sporty mooring kind of locations. So this is the ranking of the ship track resulted from our study, and based on all this ranking of mooring and bioargos and ship track, we recommend few tracks can be recommended as immediate. For example, this is the picture. So we say that the locations of recommended Rama plus Omni mooring and sorry for that. So and the location recommended for Rama plus Omni mooring and ship tracks by the OSSC for the surface ocean pCO2 measurements are shown here. The moorings are selected based on the ranks within each basin. So these areas, if you want to start, I mean, this will be the large value addition for the Indian Ocean. Here the black dot represents the mooring location, and number of circles surrounding them shows which season they add a best value, whether in DJF or MAM or JJS or October, November, etc. So the star dot represents our recommended ship tracks if suppose somebody wants to start a SOP program for the Indian Ocean. Well, that's it. I think I'm well in time of 1 hour. So the conclusion is that using Bayesian inversion theory and incremental optimization technique and utilizing a global ocean biogeochemical model, for the first time we optimized the location of Rama and Omni moorings and bioargo floats and commercial ship tracks, all of them, okay, making measurements of pCO2 in the Indian Ocean, and that would improve our overall knowledge of carbon flux in this basin. So the cost function is minimized in such a fashion that the observations of pCO2 from these mooring floats or ship, for example, are optimal for the maximum reduction of the sea-to-air flux of the Indian Ocean basin. The results show that due to spatio-temporal variability of the Indian Ocean physical and biogeochemical dynamics and its strong dependency on seasonality, multiple mooring locations must be equipped with the pCO2 sensors to capture the variability throughout the year. And continuing, the ship track measurement of underway pCO2 in soup are far more efficient in constraining the Indian Ocean fluxes than time series data fixed moorings. So that is another message in this paper. And we say that the maximum uncertainty reduction achievable by mooring is basically 30% only in different seasons. However, the soup data is for perhaps ship data may contribute up to double the amount of that. And on the other hand, considering bioargo, we have a recommendation. One may consider that around 20 bioargos are still a right choice over installing mooring in the pCO2 sensors, but that depends upon the agency which implement it, for example, which is convenient to them. So, however, a caveat is that bioargo floats can detect pH only, while mooring can directly measure pCO2. There can be some errors also associated with those, etc. So this study therefore provides the guideline for initiating future pCO2 measurements in the Indian Ocean. So this is what I want to say, and these are the acknowledgement given to various data sources and IITM, of course, and these are the people involved in this particular work, and I thank all them for their contribution, and thank you very much. So if there are some questions I can take. Thank you, Uday. I'm done here.
Thank you, Dr. Vinu. We have some questions. I'm just pasting them in the chat box so that you can just try answering them.
Yeah, I think I first stop the screen share, and I hope I'll see the questions from the chat option.
Yes.
So I'm not sure how much I can answer, but I will try my best. Okay, so one question. I don't know who asked this question. I'm forgiving.
The first three questions are from Dr. Sharma, NIO.
Okay. Hi Sharma, how are you? So he has asked, for example, I think the model uncertainty is coming from weak mixing in the northern Indian Ocean, lack of real-time river. Well, that's a good point. River is included in this model. So the river part should be taken care well. And mixing, of course, as you know, there are some error bound to it in the parameterization. And you are very right. The fundamental model should be the least biased model to have a best estimation in any OSSE. So I agree with that. So saying that a lack of river time, real-time river discharge and atmospheric deposition. Okay, atmospheric deposition may add some mismatch between model and observation. We don't have that atmospheric deposition part in the model. So I agree with that. That's a very good comment. Maybe we should relook into the problem also considering those parts, especially in the North Indian Ocean. And the second question is that even though we may get more in situ data, how to run the model without having above said issues parameterized in model? I agree with that. Dr. Sharma's comments are very valuable. So we may have to modify the model to account for unrepresented things, just as river discharge of nutrients and the DIC, for example, and atmospheric depositions need to be considered. You are right that I strongly believe, he continues, I strongly believe that we needed to work on parameterization of new processes required to estimation of pCO2, for which other efforts are also required in addition to what you mentioned. Well, the other efforts I presume may be looking at by question 1 and 2, may be improving the models, improving the parameterization, including the unrepresented processes. These perhaps may be the other processes he is mentioning. I agree, Dr. Sharma, that's a very valuable comment. Now, the fourth question is that 40 degrees south is a very dynamic region due to high eddy activity and mixing of different water masses. Whether this has been considered for this study? Well, the data we use to run the model is a reanalysis data, which available only as monthly input. Okay, we don't have a high resolution input from the reanalysis center, so that may misrepresent the eddies. However, the model has eddy parameterization by looking at the stratification by the Gendon-McWilliams scheme and Martha-Reddy's isopycnal fluxes or skewed fluxes. So those are all already parameterized in the model. Well, they are not well represented, but they are parameterized. Okay, so this is I could say. So they are somehow parameterized. And if you look at the CFC inventories, which is simulated by the model, that's the transport verification. They are quite matching well with the GLODAP data. So they may not be. So that means the parameterization of eddies may be represented by these bolus velocities of McWilliams scheme, for example. But I'm not guaranteeing it will replace the real eddies, for example. They are still parameterized. But to answer that, looking at the CFC inventory, we are confident that especially 40 degree south belt mixing and inventory or the intrusion of the tracer is exactly matching with GLODAP. So we are confident on that point. Now he continues, I guess, can you explain more about model, about boundary condition, river discharge, any assimilation? If not, can be, I think, just a second, please. See more. I think there is a Q5. I don't know who, is it a continuation from Sharma or not? Can you please explain more about model, about boundary conditions?
That is an independent question by another person
okay,
named
fine.
Jishad.
Okay, no problem. Yeah. So he's asking, can you explain more about model, about boundary conditions, river discharge, any assimilation? If not, can we add outputs, etc.? So I think, well, these details I recommend please read the paper. All citations to these boundary conditions, forcing, etc. are given there. I recommend you read that, and rather than I spend time explaining here, you can go back and check what are the boundary and forcing conditions used in this model. Then I think, yeah, and another one came as the importance of observation location is changing. Can gliders be used? Can be used in place of bioargo and get the desired data. See, first of all, I need to take this bail that I'm not an observational specialist, so I don't know how gliders can have a sensor of pH in it. I'm not a person aware of that. So also gliders are, remotely operated. That much only I know. I don't know how, how autonomous they are. I am not very sure. So I think Argos and gliders have two different purposes. That in my understanding, gliders may look at very high frequency physics, for example, well, but Argos may look at very much more coarse but deeper and larger data scale. I don't know. So I don't know how to answer this particular question. Okay, so I think any other questions, Uday, for this particular session?
I think that those are the questions. I think you might get more in offline. In the sense, they might write back to you once they go over this lecture, wonderful lecture once again, because it's there in available in YouTube. So they will go over once more, and then maybe you'll be asked or flooded with more questions.
Okay.
I thank you for your wonderful talk. It really gave a good insight, and I also feel a lot more people will be encouraged to take up similar works, and if possible, they might collaborate with you in future in trying to resolve some of those things which you mentioned can be taken up as a future course of work. So thank you once again for your wonderful talk, Dr. Vinu.
Okay, thank you, Uday, and I thank the audience also for patiently hearing, and thank you for raising those questions also. Thank you, Uday, for giving me this opportunity through ITCO Ocean webinar, and very glad to I was very glad accepting this and doing this. Thank you for all the arrangements. Thank you very much.
Thank you. Thank you.
Yeah.
Stop listening, sir.